So Math 26, section 1.8. But before we start the section, two things. One, check announcements. I post announcements about a summer program for those who are going to be STEM major. Please look at that carefully and reach out to the counselor. I left her email right below her name in the announcement. That's the first one. There's a stipend of $5,000 for those who qualify for that summer program. If I was you, I would do it. If I'm good in math and I want to do STEM major, I would do that. The next thing is we have a math club. Okay, the math club. We usually meet every other Friday. I emailed the other person to check when is the first day of the meeting, so I'm waiting for him to get back to me. And it's going to be online for the meantime, so it would help if you are like a STEM major or if you have interest to join the club to become a member. You can put that on your resume in the future when you apply for transfer, you apply for jobs. They like to have to see that you were active on one of the clubs for social, because they want to see the social aspect behind this. Even as a member, probably you might want to be the president or the vice president. So if you would like to be added to the Canvas shell for the math club that I created right before the semester started, you can email me and then I will add you as a student so you can see all the announcements, all the stuff that I put in there. So please email me. That's another thing. And today we're going to cover section 1.8. Introduction to linear transformations. I'm assuming you did 1.5 and 1.6, which would be okay for these two sections, but for the future sections, very important. 1.5 and 1.7. 1.5 and 1.7. So this talks about linear transformations. First we start, I wrote this down already. So the matrix equation AX equals B. What is AX equals B? What is A here? A is a matrix. So this is matrix. This is a vector. Okay, this is a vector. And this is a vector. So this is AX equals B. So what this is saying, it's kind of like when we did with functions. So it says it can come up in a different way where functions are defined by matrices. So if you remember when we did f of x, it give us something, right? Something, some function here. So what f did, it took x and it give us something out as an output. So here, instead of function, I'm considering A. A is a matrix, so A plays a role as a function. A times the vector x gives us another vector B, A, B here. So in general, if we are given m by n, this is called m by n matrix A, or sometimes we write it like this, A and subscript m times n. We say m by n. So m by n matrix, we define the function, okay, we define the function T that maps Rn to Rm by the rule T of x is Ax. So what T does, the transformation, or this T for now, I'm going to call it, T takes the vector x and produces a matrix times the same vector. So this is called, this Rn is called the domain. This is called domain of T. This is called codomain of T. So again, what this does here, T of x, T takes vector x, okay, vector x, and gets it multiplied by a matrix. That's what this is saying. It takes that vector, gets multiplied by a matrix. If we look at an example, let's say A is given as 3, -1, 0, 6, 2, -5. we define T as R3 to R2. And I will come back later, comment more on those superscript, the 3 and the 2. Okay, so what I'm going to do is I'm going to take a vector x. Okay, vector x. I'm going to take t of x. But what is x? Well, let's take it as whatever you like. 1, 2, 3 maybe. 1, 2, 3. So the transformation or the mapping up there on the top of the page, it says you get A times X. So I take the matrix A times X, which is 1, 2, 3. And then what do we get? To multiply matrices, this is 2 rows by 3 columns, 3 rows by 1 column. So I'm expecting, because these match, I can multiply. I will end up having 1 by 2 matrix. 1 by 2. So let's multiply that out. How do you multiply that out? You multiply row by column, row by column. So row by column, what do I get? 3 times 1, 3, plus 0 times 2, 0, plus 2 times 3, 6. So I'm done with the first row. Now I multiply the next row by the same column. So negative 1 by 1, negative 1, 6 by 2, 12. Negative 5 by this, minus 15. Combine, you get 9. What else? 9, negative 4. So what happened here? We did t of x. I took a, multiplied by x, and give me a vector b. These are vectors, like that. So this thing I just showed you and before, let's write it as a note. Any function t that maps Rn to Rm is called a transformation. Any questions about this so far?
Is that matrix 9, negative 4? Is that the answer to this question then?
Yeah, this is a vector.
Right. So, okay, so that's the point of this, the T Rn to Rm.
Yeah, so what t did, it took this vector 1, 2, 3 here, multiplied by the matrix A, produces another vector B. So I call this vector B. So that's what, yeah. So that's what I started the lesson with today. If you take A multiplied by X, you get B. So that's what I'm trying to show, that this matrix equation works in the same or similar way as functions.
Okay, and so the Rn means it started in R3 and the vector, which is B, is in R2 now. Is that what that notation means?
Yeah, that's a good question. Here, see this 3 here. This 3 tells you how many columns. This tells the columns in A. The 2 here tells us the rows in A. So if you look at A, matrix A, there's 1, 2, 3 columns. Do you see them? And 2 rows. Yeah. That's what those stand for.
Oh, okay.
Yeah, so when we said R3 means I'm returning back to or referring back to matrix A that has 3 columns and 2 rows.
Right, because those N and M are subscripts are taken from the dimensions. Okay,
Yes.
got it.
So now we can write, given any vector x in Rn. Okay, so n is the later one, first one, sorry, the domain. Any x from Rn, the vector tx. You see why I call the vector? Because it's b, it's the same as b, is the image. We call it the image of x under t. And if we take all these vectors in Rn and we find t of x, then the set of all images t of x is called the range of t. The range of t, range of t. Let's look at an example. Given matrix A, 1, 3, negative 1, negative 3, 5, 7, and define T to go from R, how many columns? 2 columns, and how many rows? 3 rows. So R2 to R3 by T of x equals AX. Find the image of a given vector 2, negative 1 under T. You guys should try it first. So to find this, we find T of that vector 2, negative 1, which you take the matrix 1, 3, negative 1, negative 3, 5, 7, and multiply it by 2, negative 1. And the answer should be 5, 1, negative 9. That's the matrix B. Let's add another part to this. Find a vector x in R2, such that T of x 3, 2, negative 5. So here it's kind of backwards. They want you to find this vector if the answer is given. So how do I start this? Well, we have to take the matrix and multiply it by a vector x. I don't know what the coordinates of that is. X2, x1, x2. So this is vector x. This is matrix A. And when I multiply them together, that gives me 3, 2, negative 1. So here I'm required to solve for x1, x2. So how do we solve for x1, x2? This is T of x. This looks like a system of equations. So if you multiply the first row by that column, you get x1 minus 3x2. So you have 1, negative 3. 3x1, 5x2, so 3, 5. Negative 1x1 and 7x2. And then you have 3, 2, negative 5 as the last column. And what do we need to do here? We need to do row reduction, or apply row reduction. So you have already 1 here, so I use it to clean the first column. So how do I clean the first column? I multiply the first row, row 1, by negative 3 and add it to row 2. And I multiply row 1, or I take row 1 and add it to row 3. That will make it 1, 0, 0. Negative 3 stays the same. 3 stays the same. Then negative 3 times negative 3 is 9. Added to 5, 14. -9 plus this -7. This goes away. This is 4 and -2. What's next? Next, I want to make this 1. Yeah, good job. So you say multiply 1 over 14th row 2. I want to make that number 14 1. So 1 0 0 stays, -3. This becomes 1 stays. 3, this becomes -1/2, and -2 stays the same. So I have a 1 here. So now I take that 1 and I use it to clean column 1 and row 1 and row 3. So 3 row 2 added to row 1. -4 row 2 added to row 3. What do we get? 0 1 0 0, 0 1 0, 3 halves, -1/2, and 0. If this is okay with you guys, then x1 is 3 halves, x2 is -1/2. So that gives me the vector x 3 halves, -1/2. Any questions? Now, let me add another part. Is this vector, is vector C in the range of T? So I'm thinking about what kind of questions you can be asked on homework or exams. And I'm trying to include all of this in here. Now the question is asking, is the vector C, given vector C, in the range of T? So this means, can you find a vector x so that T of x is C? That's what this is saying. So I can say C is in the range.
Would you please repeat that,
Yeah.
the meaning of this question?
Yeah, so this is saying, can you find a vector x, okay, vector x, so that T of x equals C? So I'll write that down. So C is in the range of T if C is the image, C is the image of some vector x in R2. That is, i.e., that is, if C equals T of x for some x, some vector x. In other words, let's write again. That is, we check, that's how we're gonna solve it. We check if AX equals C is consistent. AX equals C is consistent. So I don't know what vector x is for some vector x. I don't know what it is. We're not required to find what that vector is. So A was 1 3 -1, -3 5 7 times vector x, x1 x2, 3 2 5. And now we're going to do exactly as we did in the first, in the previous part. We have 1 -3 3 5 -1 7, and here we have 3 2 5. And I'm assuming everyone can do can write this using row echelon forms, and that would give us 1 0 0 0 1 0, and here we're gonna get 0 0 1. I recommend you try it now and make sure you got the same answer. So let's go over the reduced echelon form here. So I take row 1 multiplied by -3 added to row 2. Then I take row 1 added to row 3. 1 0 0 -3. -3 times -3 is 9. Added to this is 14. -3 by this -9 plus 2 is -7. And when we add it, you get 0, you get 4, and you get 8. So now I take 1/14th row 2. 1/14th row 2. So 1 0 0 1 -1/2. This stays the same. Now I use this number to clean up the second column. So 3 row 2 added to row 1, and -4 row 2 added to row 3. Let's see. 1 0 0 0 1 0. So 3 times -3/2. Oh, that gives us some fractions here. -3/2 added to 3. So -3/2 added to 3, 3/2. And this stays the same. And for the last one, -4, this is 0. And -4 times -1/2 is 2, plus this is 10. Okay, so yeah, we got a slightly different answer there. But,
yeah, that's what I have.
Yeah, so what happens here is we look at the last row here. You see how we got 0 10? 0 10, that tells you this is inconsistent. So we say C is not in the image of T. In the previous part, we got 0 equals 0, so we were fine here. We're fine. But as soon as I change, as one of you noticed, I changed the -5 in the previous one into 5. Same vector, but I just changed, I dropped the negative sign. Yes.
So in the last part, we cannot divide row 3 by 10. And
you can, yeah, you can. You will get 1 here. So you still have
So-
0 equals 1.
oh, okay.
So still inconsistent.
Okay.
Now special transformations. Special transformations. If we let matrix A 1 0 0 0 1 0 0 0 0 and T of x equals AX. Always mute your microphone after asking questions. So now what we have here is T of, if I take x1, x2, x3, and I multiply it by this 1 0 0 0 1 0 0 0 0 by x1, x2, x3. What do we get? Row by column. That gives me x1, 0, x2, and the last one 0. So what this does, or what happens here, because this is 0, what T of x did, so this is xyz plane, and say we had a vector x here. What a of x did, it took x and it projected down in the xy plane. It projected down in the xy plane. So what this again did, it projects, because the z coordinate is 0, it projects R3 onto the xy plane. So that happens when the last column and the last row are zeros. Then it projects a three-dimensional vector xyz components into the xy plane. Also good to introduce what we call identity transformations. So the transformation T of x equals ax when the matrix A is 1, 0, 0, 1 is called identity transformation. And if we have given a matrix, m by n matrix, the matrix transformation, just quick definitions here. Matrix transformation associated with A, with matrix A, is T of x equals ax. That's the one I started with today's lesson. And since we're talking about matrix transformations, we have some properties of matrix transformations. So it says, if you have T of u plus v, you can get T of u plus T of v for all u and v vectors taken from Rn. They belong to Rn. Or before I do this, let me explain why this works this way. So if I want to find T of u plus v, remember the transformation T, it gives me ax, so a times u plus v. So that's au plus av. But au is T of u and av is T of v. So that's why it works. The second property, T of cu. You can pull the c out and just find T of u for all u in Rn and all scalar c. Those are the properties of matrix transformations. Also, as a definition, a transformation T that maps Rn to Rm is a linear transformation. If two things, T of u plus v is T of u plus T of v, as I showed in the matrix transformation, for all u and v taken from Rn. T of Cu, Ct of u, for all u in Rn, and C scalar. So again, this is associated with linear transformation, which we're going to be using this throughout the semester. So we can conclude that every matrix transformation is a linear transformation. So we end this section by adding more properties, other properties. The first one, if we suppose that the T maps Rn to Rm is a linear transformation. So when I say suppose, then the two properties applied. So then T of 0, so T of the vector 0, that will give you 0 vector. And why is that? If you like to see, you can write T of 0 vector as T of 0 times 0 vector. And by one of the properties, this is C. It's like the scalar multiple. So C times T of 0 vector. And that gives us 0. That's why. And the other property, if you have not just Tu plus V, Cu plus dV, where C and D are scalars, you can take the C out T of U, take the D out T of V, for all U and V taken from Rn, and C and D scalars. And if you like to look in the general case, in general, for all vectors, V1, V2, all the way to Vp taken from Rn, and scalars, C1, C2, all the way to Cp, we have T of C1, V1 plus C2, V2 plus all the way to Cp, Vp is C1 T of V1 plus C2 T of V2 plus all the way to Cp T of Vp.